So RTL verification guy will test that particular thing. So there will be some kind of back and forth over here. So RTL verification guy will find some bugs, will report to the RTL design guy. Okay, RTL designer will change something, and again it will be coming to the RTL verification. So some kind of iterations will happen over here, and after that, once it is stabilized, it will be then going to the next step, which is nothing but my synthesis. So here synthesis, we will be converting that high level language we call Verilog is like high level language, right? So we'll be converting that to my gate level language. That means the functionality with the help of logic gates. So we have kind of RTL design, which is high level language Verilog. In the Verilog code, HDL code we have, and that will be converting into the gate level design. So that means we'll be converting that to gate level design, and that's what happens at my synthesis stage. So the next one is like DFT. I can say DFT, the work of the DFT guy will be divided into two steps. So first is before the synthesis and after, and the other one is after the synthesis. So here at the DFT, what DFT, I can say it's a design for testing. So I said you right. So I think at this point of time, I wanted to say one, like say the motivation for me to come into this field. Okay. So everything can be we can repair everything. Okay. So one back when I was in my BTech or something, I kind of faced an issue with my laptop. He said I take it to the like say technician. He said that he has some issue related to my processor. So I asked him to repair it. Okay, he said he laughed at me and said that what you're speaking, we cannot repair the processor. But then I kind of developed this kind of like say what do you say enthusiasm to know what is actually present inside that, and why can't we repair this particular guy? So when we are able to repair everything, why can't we just repair this guy? So then that's kind of motivation I have, and I think you might be knowing the answer for that by now, because like the processor, what the kind of transistors which we are using inside the processor is very minute. We cannot even see with our naked eye. So if something goes wrong inside that, that's it. We just need to throw it away. We cannot just repair that. We cannot if at all something needs to be repaired, it needs to be repaired in the process flow. That means in the fabrication flow itself, something needs to be repaired. So that's where I mean I kind of developed that GLR enthusiasm to come into this field. And now one of the steps to make sure that chip is fabricated properly is my DFT. So design for testability. So you fabricated one chip, okay? So you fabricated one chip, and you wanted to make sure that if that chip which you have fabricated is working properly or not. So for this particular reason, okay, so you will be having or you will be adding some kind of logic into the design. So and that logic you call it as design for testability. So once the chip is fabricated, so the at the fabrication, as soon as it is fabricated, one guy will be sitting over there, and he will keep on like say he'll keep on identifying if which chip is working properly and which is not working as per the expectation. That means whichever is meeting my functionality and whichever is not meeting my functionality. We'll just discard the chips then and there itself, and how it is possible? It is only possible with the help of this DFT step which we have. We'll be having the DFT engineers who is the kind of like say they have very peculiar requirement or peculiar work over here. So they kind of need to add some related logic. So in order to either once the chip is fabricated, in order to ship it to the customers or discard that. So based upon the logic which this guy has added will be decided. And then coming to my regular PNR steps, so which is flow plan. Okay, so okay, fine. The flow plan. Okay, so you will be having okay, you might be aware of the macros. Okay, so if at all you have used any Outlook or Gmail or any other thing, maybe in the C language also, you'll be having the macros. So what is a macro? So macro is nothing but whenever we wanted to achieve one kind of functionality and we wanted to achieve that functionality repeatedly. Let's say you want half adder or full adder. Okay, so you kind of develop one code and keep it ready whenever we require that. or else let's say kind of procedure or system. Okay, so we can just call that function. We can just call that function and get that job done, right? So so that's the kind of we will be having such kind of procedures or functions inside my ASIC design or integrated circuit as well. For example, let's say you wanted to store some amount of memory. Let's say you wanted to store 1 MB of memory, 1 MB of data. Okay, so we will develop, we'll kind of develop a macro. Okay, we will hard code that. That means we'll be developing it upfront, and we'll keep it ready. So that means whenever we need that, we'll just instantiate. That means we'll just call that and we'll use it. So we'll be having such kind of macros in my design, and placing those macros in some respective locations is what we call it as the floor plan. So I can show you, I can draw you the diagram. So how my floor plan or how the floor plan may look like. Okay, so let's say this is my complete chip. So might be having some of the macros, and we wanted to, so these rectangular shapes which I'm going to draw, which I'm drawing is called as macros. So we'll be placing the macros here like this. So let's say, so this is like 1 MB of RAM, this is 1 MB of RAM, this is 1 MB of RAM. So let's say we need 4 MB of RAM. What we'll do, we'll keep 4 such instantiations. So that means we'll use 4 such macros, and then we will do the floor plan. So that means placing of these macros on the code area, okay, on my, on the chip is what we call it as the floor plan. So that is what we will do as part of this floor plan step. Okay, and then coming to the placement. So in order, typically I said you before, VLSI is like around 1 million of instances, 1 million of logic gate or transistors will be present. Okay, so now when we have that such kind of 1 million of gates, can you hand place all of them? It's nearly impossible, right? To place all of them in the hand place. So it's nearly impossible. Okay, we'll be making use of some kind of tools here. Okay, in order to have this kind of functionality, in order to do this particular thing, okay, we'll be making use of some of the tools over here, tools or softwares, whatever it is. So we call them tools over here in the VLSI flow or in the VLSI world. So one such tool is like, I can say ICC2, IC compiler, or the Encounter, Innovos, or Talos, and we have many other tools. Okay, all these tools are used, okay, in order to achieve our functionality, or in order to achieve our task. The placement is one of the flow or one of the step where we wanted to place such transistors, more than 1 million of transistors we have in our design in the on the chip. We'll make use of the tool. The tool will place all those transistors on the chip like this. So it's like I cannot draw all of them. It will be something like this. We can all these small ones, we can call it as gates or transistors. Okay, so all those things will be placed by my placement engine. You will be having many such things on the design with the placement. So we kind of place all these things on the chip. Coming to the next one is the CTS, clock tree synthesis. We will be using some of the memory elements in my design. So some of the memory elements like flip-flops, latches in the design. Okay. When we use the flip-flops and latches, one of the important signal which is needed to that is my clocks. We want everything to be synchronous inside that, because all the kind of communications which we have inside my design, if it is not synchronous, we kind of cannot estimate when we can see the output. Something is being processed over here, something is being processed over here in the chip, and from this chip it needs to communicate to the outside world. So we'll be kind of providing inputs to it, and from the based upon the inputs which is received, we should be kind of providing necessary signals, or we can kind of pass on necessary signals to the output world or the outside world. Let's say you have a processor inside your laptop. We kind of need to provide the necessary signals to your display. Okay, display controller will have. We'll be providing necessary signals to the display, saying that okay, this is what you wanted to display. This is what the pixel which you need to light up. Or let's say, let's take the case of your speaker. So this is what the bit you need to pump out. Okay, so that means like a processor is kind of providing necessary signals to all the peripheries which we have outside of your processor. So when we don't know when exactly we will be receiving the output over here, okay, we cannot give a necessary or correct signals to the outside world. So that's the reason we want everything here to be synchronous. Let's say we use kind of two, let's say I'm drawing some of the flops over here. Let's say typically we'll be using the D flip-flop. So these are the three flops which we have. So from this input, it is going to the flop, and from this flop, it's going to the other flop, and from this again, it's going to the other flop, and here it's going to the output. We should be providing the clock signal to this. We'll be providing the clock signal to all these flops. And now we can say, once we provide the input over here, after 1, 2, 3 clock cycles, we can see the output. I provided the input now. After the 3 clock cycles, we kind of see output. So if we have this kind of data, we can easily or we can easily communicate whatever we want to the outside world. So we'll be having various kind of protocols. That's the other part of the story. How to communicate with particular thing, how to communicate with one particular device or periphery. We'll be having some kind of protocols. So that's the other part of the story. But everything needs to be synchronous. So what my main point here is to say you guys is that clock is the main signal which we have over here, and which will keep every logic or every logic in my design synchronous. So we'll be using the flops and we'll be providing the clock signal to all of them. Let's say my clock period, I think you know clock period. So I will be drawing the clock signal over here. Okay, so you know D flip-flop will be reacting to the rising edge. So whenever we are having the rising edge, my D flip-flop will be reacting to that. So from here, the time taken, the time in between this rising edge and this rising edge, we call it as the clock period. Let's say it's 1 minute. Okay, from here to here, let's say it is 1 minute. Okay, that means after 3 minutes, we can see the output over here. So we have provided some input. After 1, 2, 3 minutes, we can see the output over here. Let's say this clock signal, which is reaching this particular flop, is kind of delayed. Instead of seeing the clock signal over here, this person might have seen the clock signal after some amount of time. That means after instead of seeing the clock signal at second minute, you might have seen after 2.5 minutes, let's say 2 minutes 30 seconds. What happens now? The output which you wanted to see over here will be kind of delayed. Not to see such kind of complexities, we'll be doing the clock tree synthesis. The clock tree synthesis is the one where we will be providing the clock signal to all the memory elements in my design at the same time. So we kind of provide clock signal to all the memory elements in my design at the same time, and that is what we do as part of my clock tree synthesis. Again, we'll be making use of the tools over here, so which will kind of help in achieving my functionality. So which is to provide clock signal to all the memory elements in my design at the same time. And then coming to the next step, which is nothing but routing. Over here, so far till this point of time, we don't have any physical connections in between two logic gates. For example, let's say we have communication from this person to this person. It's only logical connection we have till this point of time, till the CTS. At the routing stage, what we will do is we'll make use of some of the metal shapes. We'll make use of some of the metal shapes, and we kind of connect these two gates. This flop and this flop will kind of connect with the help of some metal shapes. So we can either use copper or anything. We'll be using the copper most of the times. We can even use the gold in some cases. So from here to here, so we'll be using the copper, and we'll be kind of making the communication possible. So that means till this point of time, everything is logical, but after this routing, everything is now physical. So that means even the signal will be now able to pass from here to here from through this metal shape. And then coming to my sign off. So sign off checks, what we do over here is we'll be having some kind of sign off checks. So for example, say we wanted to achieve one functionality at the end of the process. So did we really achieve that functionality or not? So that is what we check as part of the sign off checks. And then coming to my fabrication. So here the chip will be fabricated or manufactured at the foundry. So at the TSMC or Global Foundry or any other some foundries. And then packaging and testing. So once it is fabricated, it needs to be properly sealed in the ceramic packages or plastic packages. Nowadays, we are only using the plastic package. You might have seen the processor. It will be coming in. It will be enclosed in one plastic or ceramic package, and you'll be having the ports coming out of that. You'll be seeing some of the metal wires coming out of that, and that is what we call it as the package. And testing will be also happening at the same time. So we'll be once the chip is fabricated and it is coming out of the foundry, we'll pack it and we'll test it. We'll test the functionality of that. So you might be seeing some of the gamers available on the, so you might have seen some of the gaming requirements. So the person will keep on, will be sitting in front of the laptop and he will just need to play the games. So here, what we do here in the background is we call it as the testing. So what is the promised frequency? What is the promised performance we have? And when the particular gamer is testing that, we will be kind of analyzing some things in the background saying that, okay, we wanted to have this, achieve this kind of performance. Are we really achieving this performance or not? So we'll be doing the testing in the background. So so that's the reason, like say they even employ some of the persons just to play the games. So that is, that's the reason behind it. So they're just testing the chip in the background. And then we have the final check. Once they say that everything is as per the expectations, and then they will be shipping to the customers. So we have the chip and that will be shipped to my. So I think it's like a pictorial representation of what I've said so far. So I think I will just skip this particular one, keeping the time in mind. Okay, importance of the physical design engineer. I think I've said to you, I am a physical design engineer. So aim of any PD engineer, PD in the sense physical design engineer, is to realize the logic. PD engineer will be kind of receiving the input in the format of Verilog or logical information. So high level language, he will be receiving that, and then he is the person who is realizing that logic. So everything will be on the everything will be on the language, high level language, right? So now the PD engineer will just realize that logic. So he will just convert whatever we are having in the logical format to the physical format. That means we can even really achieve that functionality. So we have something logically, and we have to convert that to physical format, and that is what we call it as that is what the role, or we call it as realization of the logic, and that is what the aim of any physical design engineer. So time to market plays an important role in the VLSI industry, and PD engineer plays a crucial role here in this aspect. So because, okay, I just want to go one slide back here. So here I said you right. So RTL verification guy will be verifying that design, and he will be providing that to my RTL design guy. Okay, now see if anything he found out late. For example, say he found out something very late in the process. Okay, he didn't find out all the bugs in the design, but after later on he kind of found that bugs. Who is the person who is going to suffer now? Obviously the physical design engineer, because the RTL verification guy haven't done his job properly. That's the reason at the end of the day, so PD engineer is the one who is going to suffer here. That means he found the bug late, and we are responsible. The PD engineer is responsible to incorporate that bug, but still we need to deliver the product on time. What I mean, because for example, most of the chips will be released into the market. Let's say we have back to school season. Okay, back to school season, when it comes, what happens? And then we will have all our kind of products in line. It should be readily available in the market, so that the customer can pick whatever is present on the board. He can pick and choose whatever he need, and he can buy that out. So, but once the back to school is done, okay, so time to market plays an important role. For example, say we have some of the products on the board. I mean, for example, let's say we have to release some products before March, because let's say that's the time when majority of the schools will open, and they kind of like say pick and choose some of the products, let's say laptops or computers or mobiles or whatever it is. They wanted to buy some of them. So if the product is not readily available at that point of time, what happens? So we are losing our market. There is no customer who is going to buy our particular processor. So that means it's a loss. It's a tremendous loss or huge loss to my company. So that's the reason the time to market plays an important role or crucial role. So PD engineer is the one who has to take all the pressure. If at all any mistakes has happened before reaching his level, so he has to incorporate or accommodate all those mistakes, and still he need to deliver the chip to the market on time. So that's the reason PT engineer plays a crucial role. Then responsible for delivering data to various stakeholders. So we PD engineer, like he'll be kind of designing, physical designer. He will be designing the particular chip, and he will be responsible for providing that to various stakeholders. He needs to let's say package and testing team we have. Okay. We need to say them that this is the size of my chip going to be, because they need to develop or they need to also design his package. So we should be kind of saying him, so this is how, this is what the dimensions, this is what the length and breadth of my chip is going to look like. So once we have committed to that length and breadth, we need to abide to that. Okay, we cannot change that at any point of the stage later, because that's going to again kill his time and also the time to market. So we'll be kind of responsible for delivering the data to various stakeholders. That means we need to deliver the data on time for enabling many other linked works. For example, let's take the case of packaging. So then he needs to start his work. So we need to deliver him on the time. So that's why we can say like we responsible for delivering data to various stakeholders. Responsible for multiple sign-off checks to make the design depot ready. So this is the person who is going to say, yes, the chip is ready. We have realized that logic. You can now fabricate. That means you can assume the amount of burden or amount of pressure or amount of the checks which he needs to do before saying that we have realized the logic. Now you can fabricate. That means he needs to do multiple sign-off checks in order to make sure whatever he has done is correct, and he has realized that logic complete. So that's the reason like he has to do multiple sign-off checks in order to say that the chip is ready for tape out. So when I say tape out, so it means we are now going to fabricate this. So that's what we call it as the tape out. Okay, so I want to cover some of the latest trends in the lower technology node. So one such thing is the MBC FET. So you might have seen the gate all around where we have using the nano wires. So this is the latest technology from the Samsung. So he is using the nano sheets. So instead of using the nano wires, he is going to use the nano sheets over here. So it's like a multi-bit channel field effect transistor. It's from Samsung, and it is a gate all-around structure, but with nano sheets. Instead of having the nano wires, they're having the nano sheets. So he will claim that the drive currents will be more and faster switching times, and the functionality, or they have better performance over here from FinFET compared to the MBC FET. And the other one is the 3D chip. Okay. We so far, let's say you might have seen CPU and the graphic processor separately. So the graphic processor might be sitting a little bit farther from my CPU. Okay, then what happens? Like there might be having some kind of 1 centimeter or 2 centimeter gap in between your CPU and your graphic processor. I don't believe this 1 centimeter or 2 centimeter gap can make a huge difference, because you kind of embedded millions of transistors in that 1 centimeter area, and now it has to travel that 1 centimeter distance in order to reach your graphic processor. So that's going to add huge burden. That's going to have like huge performance loss. So now we kind of came to this 3D chip architecture. Above we can see one die 0 and below we'll be having that die 1. So we can say graphic processor or CPU above and top. Instead of going all the way on the motherboard, we can now have a die 0 on the top, die 1 on the bottom, and we can kind of communicate using the TSPs. We call it as through silicon vias. This is one silicon, die 0, and die 1 is the other silicon. We kind of having communication from this chip to this chip, that we call it as through silicon via. So that means one chip above the other chip architecture is the latest trend which we have. With the help of TSP through silicon via, we'll communicate across the chips. Accessing a processor by the peripherals will become easier with this kind of approach. So we can, I mean, it's going to reduce that whatever may be the distance which it needs to travel on the motherboard here now. So that's going to increase my performance as a whole. Okay, monolithic 3D chip. I will be discussing this in the next in the case studies. I wanted to like say these are some of the case studies which I have. The first one is the self-catered register. The power consumption by my processor is mainly because of the switching power. Switching power, we call it as the dynamic power. So you have the clock signal which is actively switching in between 0 and 1. So we call it as the switching power, and clock signal needs to be clocked many times. I mean that means it needs to go to 1 0 1 0. It needs to toggle like this forever. So majority of the power consumption is because of this clock, because of this dynamic power. So what we have come up with is like the self-gated register. So we will be kind of having one register. Okay. So we'll be having the D input and we'll be having the Q output. Q is the output and we'll be having the D input. Whenever the data, the input is changed, for example, you know in the digital world, we only deal with 0 and 1. So if the D is 0 and if the next signal which is reaching this point is still D, do you think that we need to enable this clock? Do you think that we need to store a different data? No, right? If the previous data is 0 and the current data is also 0, we need not to store anything addition or anything extra in my register. So that's where we have come up the self-gated register. What it will do is it will just compare Q and D. If there is any change in the D input and output, only then it will kind of take the clock signal. If there is no change in the D and Q, it need not to receive any clock signal and it need not to perform any operation. And that's how we kind of reduce our dynamic power consumption here. So this is one kind of case study which we are using, and it takes some time. It has some of the complexities involved in this in order to realize this kind of thing. Okay, so yeah, I think that is what I've discussed, self-gated register. We can move on to the next one, triple patterning. So as the technology node is shrinking, okay, as the technology node is shrinking, width of the metal layers are reduced and fabrication steps has become a challenge. For example, let's say we are having one metal shape of width W, and we are having the metal shape of width half W, let's say half of it. So fabricating this particular guy will be very much complex compared to fabricating this metal shape. That means like as the technology node is shrinking, right, we kind of having more complexities involved in kind of fabricating this one. So what we have come up with is the triple patterning. So in order to prepare one particular metal shape, we kind of use 3 layers, 3 masks. I think you might be aware of mask by now. So I have given you some glance about mask during the fabrication steps. We'll be using kind of 3 masks here now. So in order to fabricate one particular metal shape, we kind of use 3 masks. So when we use 3 masks, that means we call it as the triple patterning, and that is the latest technology trend we have. So yeah, so this is one of the advancement which we have as part of the fabrication process. In order to fabricate one layer, we'll use 3 masks now with triple pack. Monolithic 3D chip. So in the 3D chip, resistance offered by the TSVs are known. The TSVs is kind of through silicon vias, which we use in between two dies, to silicon. So then the resistance offered by the TSVs are more. We kind of have some kind of loss, signal loss over here. So instead of fabricating two chips and connecting them using TSVs, we can form two active device layers on one wafer to reduce resistance and delay. So that means we can now form completely, only one crystal will grow, and in the one crystal, we kind of enable our design process or fabrication process in such a way that two devices are formed, two transistors are formed, one above the other. In such, I mean, when we are able to achieve this kind of thing, what we can say, we kind of eliminated that TSVs in between. So with this kind of architecture, monolithic 3D chip architecture, I can say we kind of save or increase the performance. Again, this is a case study, and this is still it takes more time to realize this particular thing. Many engineers or PhD guys are working on this to realize this. Okay, so the next one, job opportunities. So these are the list of the companies which we have over here, so that after successfully or after you undergo some of the training, VLSI training, you can apply to various companies which are listed over here. It's like very short list. We have many other companies in the market. We can apply to them. We can, like say, we can get into one job role. So some of the roles like front-end engineer is the person who is going to develop the logic, verification engineer who is going to test the logic which front-end engineers has developed, and the physical design engineer who is going to convert the logic into the physical format, realizing the logic, and the DFT engineer who is going to enable the testing process once the chip is fabricated. Now the product companies like this over here, startup companies, service-based companies, and the tools related companies. So Synopsys, Cadence, Mentor Graphics, and Apache Design. So these are some of the companies who will provide the tools or softwares required for us to go through this PNR process.